everyone. In today's video, we're going to work with the model training and tuning portion of the of our project. Previously, we actually did the feature engineering, and we based on the variance inflation factor, we actually selected our feasible columns to, train our model. And initially, in the model training section, what we need to do, we need to create the training testing split of our data set. So there would be 4 different data frames or tables, like 2 for training, like this X train. This means that our independent variables training dataset, and Y train is the dependent variable of our training dataset. Similarly, this one is the independent variables of our testing dataset and dependent variable of our testing dataset. So how we are actually doing the train test split? So we are actually using a function here that is called train test split, and based on the function we are providing our original independent variables table and our original dependent variables list, and we are providing that the test size would be 30%. So this means the 70% will be our training dataset, and this is a random state. So random state is 10. So if you want to reproduce my exact results, so you can actually use random state equals to 10. Okay, but if you use anything other than anything other than 10 here as a value, then you will get like a different type of results. Why? Because this trended split is actually based on completely random thing. Okay, but if you want to reproduce the same results, then you can use the random state 10. Then it would save the specific split under this random state. Okay, so after running this portion of the code, so we can see the shape of each of our data sets. So in the X train, that is independent variable of our training dataset, we have around 35,000 rows and our 17 independent variables. Similarly, for the testing dataset, we get around 15,000 rows and 17 columns. And similarly, for the dependent variable, we get around 35,000 rows and 15,000 rows for the test dataset. So at first, as this is a regression based problem, so we are implementing the linear regression model here. So at first we are saving the linear regression model in a variable model LR, and after that we are now fitting the linear regression based on our training and training dataset. Okay, independent variables and dependent variables. And after that, so after finishing the training, we are actually generating the accuracy of the fitting. Okay, so we are actually generating the accuracy based on the testing data frames and also the training data frames. Okay, and here we can see that when we are implementing the linear regression on our training dataset, the accuracy score, that is actually r square, the value of r square is around 0.928. Okay, similarly for the testing data frame, or that for the testing datasets, the r square is also quite similar, that is 0.928. So what does the r squared actually means? So this means that around 93% of the variability in our dependent variable, that is our insurance premium prediction, insurance premium price, to predict that dependent variable. So 93% of the variability in that variable is explained by all our independent variables. So this is what our training score is saying, and also this is what our test score is also saying. But now the question is that why am I showing both training score and testing score? So this is because suppose suppose your training score is very high, like 93%, but your testing score is pretty much low, or like around 68% or 70%. So this would indicate that your model is overfitting your training data sets. Okay. But in our case, we can see that both our training score and testing score are same. So this means there is not any kind of overfitting happening in our in both our training datasets and testing datasets, and our model is actually accurately doing its job. So after that, not it is actually not like enough to get the accuracy score based on R square. We will also have to consider the error scores, like mean squared error and then root mean squared error. Okay. So to generate the mean squared error, so at first we actually need to calculate the predictions, and we are saving the predictions in a variable that is ypred. Okay, so we are actually calculating the prediction based on our this linear regression model, and we are saving it inside this y_pred, and after that we are calculating mean squared error. So at the moment you see the mean squared error function, this is actually coming from sklearn.matrix library, and this is actually working, but for some reason like the pylons, so this is actually an extension inside VS Code. So pylons is actually wrongly marking mean squared error function as deprecated. So that is why you are seeing this like a delete sign, or you're seeing this line between mean squared error, but this is actually working just fine, so don't worry about it. And after calculating mean squared error, we're saving it inside MSE_LR, but MSE is not enough. We can also calculate root mean squared error. That is basically just the square root of this value. So here we are using numpy's square root function to calculate the root mean squared error, and after that we are printing both the error values. So mean squared error is around 5 million and okay 5.1 million, and the root mean squared error is around 2272. Okay, so this is the root mean squared error for linear regression. And now what we actually need to do, we actually need to generate the feature importance chart to see what independent variable is actually working more, or is actually contributing more to predict our premium price. Okay, and for linear regression there is actually no simple function to generate the feature importances. Okay, but here's the thing is that when we are actually implementing linear regression, we get two separate entities. So the first one is intercept values, and the second thing is the coefficient values. And if we use our model name dot coef underscore, then we get actually the the coefficient values. So we actually get coefficient values for each of our independent variables, and these coefficient values means the amount of impact the independent variable has in order to predict the dependent variables. Okay, so these are also used as feature importance. This will indicate to our feature importance, like the higher value, the higher value will indicate that that feature or that column is actually have more importance or have more impact in predicting our premium price. Okay, so for that what we are doing, we are saving this model underscore lr dot coefficient or coef underscore, like this array, inside a variable named feature importance. But if we need to show like this kind of bar chart, we need to create a data frame, and for that we are creating a data frame using a pandas.dataframe function, and here we are inputting the feature importance variable here, and as index we are providing the the column names. We have all our independent variable column names, and we are like the column name will be coefficient. Okay, so I can show you separately like how it looks. So let me do one thing. So let me just copy this thing. So you see, so these are actually the column names, and these are the coefficients generated by our regression model. Okay, and as we have our column names in the index, we can easily now generate our bar chart here. So to actually see the bar chart like in descending order like this, so we are sorting our data frame using the sort values function, and we are sorting by the coefficients, and ascending equals to true. And after that, we are using matplotlib to plotting the bar chart. Pretty much self-explanatory. I'm actually not going deep dive here to explain the plotting code. So here now from the plot, feature importance plot, we can see that insurance plan and age are the topmost important independent variables that are impacting uh, the premium price prediction. Okay, and on the third we have our normalized risk score and BMI category, obesity, smoking status regular, and all other things. Okay, so these are our main, our most important features. So similarly, we are now implementing another model that is a ridge regression model. So ridge regression model is basically, so it's actually based on a regularization technique, and using that technique we get two types of regression model, and another one is a ridge regression model. And for this project we are actually implementing the ridge regression model. So similar to the original linear, this is also very easy. We are using our ridge function to, just like our previous linear regression model, we are calculating the test score and training score using the ridge regression model. So from the ridge regression model, we can see the same results of R square for the training dataset and also for the testing dataset, that is around 92.8 and 92.8%. And also after that, yeah, so same thing is here. We are also calculating the mean squared error and root mean squared error for ridge regression. So, and you can see that the root mean squared error and the mean squared error is pretty much similar with the original linear regression model. And also when you are actually following this project, you can implement multiple regression model like regression trees, or you can use a decision tree here. I will use a very sophisticated, powerful model, that is XGBoost. And in order to load XGBoost in our Python, we need to import the XGBoost regressor class from XGBoost library or package. Okay, after that what we are doing, we are actually saving the XGBoost model, and we are using 20 trees and max depth equals to 3. So these are the parameter we have provided to train our XGBoost model. After that, we are fitting our model based on our training dataset, and also after fitting the model, we can see that the test that on the test dataset, the R square value is around 97.8%. Okay. So for the XGBoost, the accuracy actually improved from 92.8% to 97.8%. Okay. So this is a huge increase. Similarly, we are generating the error values like mean squared error and RM and the root mean squared error values. So you can see the root mean squared error value is 1250. That is half less than previous root mean squared error values. Okay, and another thing is that the less the error values, the better it is. Okay. And now we are actually doing a randomized search cross validation method But for that, what we are actually doing, we have set like some um, some number of estimators the XGBoost can use. So here in the number of estimators or number of trees XGBoost can use is 20, 40, 50. And the learning rate I have provided like 0.01, 0.1 or 0.2. And the max depth I have provided like 3, 4, and 5. Okay. And in the randomized search CB, I am saying that number of iteration is 10. So what does this actually mean? So, you know, using using these values, uh, there could be like a combination of models. Okay, like one combination of model could be a number of estimator is 20 and learning rate 0.01, max depth is 3. Another could be 20, 0.01, 4. Another could be 0.015. Another could be 20, 0.1. Okay, so all those are actually combination, and among those combinations, what randomized search CB will do, it will randomly choose the 10 combination, you know, to do the reproducibility, the result I am getting from my analysis. If you want to get the same results, you can use the 42. And n jobs is equals to -1. So this is basically I'm like directing my Python programming that to use all the available CPU or processor cores uh, while implementing this while implementing this high model work. Okay. And another thing is that you can actually use ChatGPT to understand all the different arguments, different parameters, meeting. So here I just copied the whole line, and after that I'm asking ChatGPT that what does actually n jobs equals to -1 mean, and here it actually answers me very nicely. This setting tells the algorithm to use all available CPU cores on your machine to parallelize the computation. So this is basically to enable the multi-core functionality of my computer to speed up the model process. Okay, a lot of rant. So after that, here the randomized search CB, we are getting the R squared value is 98%. Okay, without the randomized search CB method, when we are actually using the XGBoost directly using 20 estimators and 3 max depth, we are getting the value 97.8%. But when we are actually using the randomized search CB, we are getting the value 98%. So as you can see that there isn't much improvement between both the model. So if you don't want to go ahead with the randomized search CB method, you are actually good to go. You don't have to implement this all the time. Okay, so after that, in order to find out that for which estimators, for which learning rate, and for which max depth we are getting this high R squared accuracy score. So to find out that, we can use random search dot best params. Then we can get the number of parameters it used, and number of max depth it used, and the amount of learning rate it used. And after that, we can save it inside a variable named best model. And the good thing about XGBoost is it actually has a inbuilt feature importance. So here what we are doing, we just called best model and then dot feature importances. Then it automatically so all our created data frame for the feature importance plot. So for that, we are creating the data frame, and in the index we are actually providing. After that, first plan and age is contributing towards predicting the insurance premium price. Because the R squared or accuracy value is 98%, that is very high. This does not mean that our work is done. We actually need to validate that if this 98% accuracy score is actually feasible enough to use in our regular in our like in the production, if it is feasible to use. So for that, what we actually need to do, we will have to do the error analysis or residual analysis. So in order to calculate the error, at first we will have to calculate the prediction values based on our best model, that is the XGBoost model. And after that we will calculate the residuals or the error values, that will be basically the the prediction value minus the actual value. Okay. And after that, what we are doing, we are also calculating the percentage. So the percentage is basically the residuals divided by actual value into 100. And now we are creating a data frame that will contain the actual value, the predicted value, the difference between actual value and the predicted value, and also the percentage difference between both the columns. And after running this, we can get, all the values here. Now, now to see the distribution of our error, that is the diff percentage, we can actually, what we can do, we can actually plot a histogram here. So here we're using the cbon function and cbon package and histplot function to plot the distribution of our errors. And here's the thing: when you are implementing a regression model or any kind of machine learning model, the residuals should be normally distributed. But here, as you can see, that the residuals are actually not normally distributed. There is actually a right skewed. The distribution is actually right skewed because we can see a lot of values are actually incorrectly got predicted. Okay. So what does the zero diff percentage mean? This means that the actual prediction price and the predicted prediction price is same. The more the difference percentage, the more the more the model actually predicted the premium price more than the actual values. And the less that if and when it is actually on the minus side, this means that the predicted value is actually less than the actual value. But here is the thing, that is you see we have a diff percentage 80%. So this means there are some predicted values generated by our model that is 80% higher than actual values. So this is actually totally incorrect, and we actually cannot push this kind of model in our production, because it might work in a short term, but in the long run our production might face different kinds of barriers if we push this type of inaccurate model in our production. So for that, what we actually need to do, we will have to analyze the error values based on a threshold. So at the moment we have a total of 14,973 rows. Okay, and suppose if we consider the error threshold or the diff percentage 10%. Okay, so what this means, that we will actually capture all the predicted values that are 10% more than the actual values. Okay, and as you can see from the histogram, that that the predicted values are in both sides. Okay, the wrong predicted values are in both sides. It actually predicted less, it also predicted more. So we actually need to cover both sides. So in order to cover both sides, what we can do, we can take the absolute of our diff percentage, and now we can use like greater than extreme error threshold, that is 10. And after that we will get a data frame. We will get a data frame that contains only those predicted values that have more than 10% differences between actual and predicted values. And we can see that the shape is or around 4,487 rows are generated by our model, where predicted value is 10% more than actual values. Okay, It could be more, and again it could be less. Okay, so suppose if you want to see that what about the 50%? So let's just change this to 50%, and let's just run this again. So here you can see that around 549 rows or 549 values generated by our model that has 50% more 50% like more value than the actual value. Okay, so 50% wrong. So let us fix the thing to 10% and do the analysis. So what does this actually means? This actually means that around 30% extreme errors. We actually have 30% extreme errors, which means for 30% customers, we will either overcharge or undercharge by 10% or more. Okay, we will overcharge or undercharge the premium price by 10% or more, and this is actually unacceptable. Now we actually need to find out the independent variables and their values for for those predicted values. And for that, what we are doing, we are just using the index. So you see, the index we have here is actually similar to the index of X test X test table. Okay. So that is why we are using x_test.log, and here we are providing the index of our extreme result df, and we are saving it as extreme errors data frame. And here we are getting like all our independent variables and their values. But here is a problem, that is these values are actually scaled values, and we will need to like reverse the scaling to get the actual age values, actual number of dependents, all other things. Okay, but before reversing the scale, what we can do, we can actually like plot a histogram that will show the comparison between overall data distribution and the data distribution for the extreme extreme errors data frame. Okay, so here we're using a for loop, and we are plotting histogram. So first we are plotting histogram for the extreme error data frame, and after that we are plotting histogram for the overall data frame. And here we are getting like that distribution for all the columns. So for the number of dependents, you can see that the blue line is for the overall data set, like the overall testing data set, and the red line is for the extreme error data set. So here the number of dependents, you see the pattern is quite same. Okay, like it's dropping and then it's rising and then dropping and then rising for the overall dataset, and for the extreme dataset it's also following the similar pattern. So in that case, this is actually completely randomized, and we actually cannot figure out any kind of discrepancy happening between the overall data frame and then the extreme error data frame. After that, the income lags. Yeah, here we can also see that the pattern for the overall data frame and the error data frame is also same. Okay, so this is going to be so almost similar for all the columns. But if we go to our first column, that is the distribution of age between extreme error data frame and overall data frame, here you can see that for the error data frame, the age is constant for some time, but after that it totally dropped. So here the pattern is actually not consistent between the overall data frame and in the extreme error data frame. So we actually need to figure out that what is actually happening in the age column. But from seeing this thing, we can guess something, that is that we actually have like age data imbalance in our data set. I think we have more young aged people in our data set compared to more older people. Okay, so let's see if my assumption is correct or not. So here we are doing the reverse scaling thing that I mentioned a while ago. So how we are doing the reverse scaling method and why we are using income level equals to -1. So we are actually doing income level equals to -1 because when at the end of the feature engineering section, we actually dropped the income level. Okay. So without adding income level in our errors data frame, if we use scalar dot inverse transform, it will actually face error. Okay. So to not get the error, we are just arbitrarily setting a value under income level column. Okay. And after that, we are creating a blank data frame, and after that we are using the columns to scale. So if I show you what is inside the columns to scale, so we actually created a list that contained the columns we need to scale in our feature engineering section. So you see the feature internal level is here. So here we are reversing the scaling on our extreme error dataset. So after doing the reversing, so we are getting the actual column values. So for age, now we are getting the actual values like 23, 19, 18, a number of dependents, 1 dependent, 0 dependent, and income level is showing -2 because it will show -2 for all the values. Why? Because we had set -1 as its scaled value. So for that, when it's reversing, it gets -2. So you do not have to worry about this thing because it does not have any kind of impact on our future analysis. Income lags, we can see the actual values, and insurance plan, we can also see the actual insurance plan category numbers. And here now we can actually generate the summary statistics. And now here's the thing, you can see the median value of our age column is 22, and not only that, our Q3 value is also 24. This means like in the age column, 75% of the value ranges between 18 to 24. Okay, so there is actually a huge type of imbalancing happening. So most probably the column is a totally and right skewed distributed column. So let's plot a histogram to see if my assumption is correct. So as you can see, this is actually histogram, and as you can see that all like the maximum of the values are ranging between 18 to 25, and only I think around max 50-60 values are ranging from 26 to 60. Okay, so this is actually a huge problem. So this shows that majority of the extreme errors are coming from young age group. We may need to build a separate model for this segment. Okay, so here's the thing, that when this type of things happen in our data distribution, so what we actually need to do, so we can actually consult with our supervisor, and we can actually do schedule meeting, we can actually do discussions, and after that we can actually find a a potential solution to figure out this kind of a discrepancy. And at the moment, as one kind of solution, what we can do, we can segment our data set into two segments. So one segment will be like data for young people. This means we will segment our main data set where age is less than 25, and then we will create another segment of data set where the age is actually greater than 25. Okay, and after that we will do same analysis for young data set and for the old age data set. So here we are creating a separate data frame, that is df underscore young, where so we are creating like two separate data frames, df underscore young, where age is actually between 25 and df underscore rest, where age is over 25. And here we can also see the shape. So df underscore young dot shape, so we can see that 20,000 rows generated, where the age is, the age is like age is below 25, and 29,904 where the age is actually above 25. And we are creating like separate Excel files for each data frame. Okay, so now so as I mentioned earlier, what we will do the same analysis for, at first we will do for the 25 and up age data frame. So we are using premium underscore rest here. So all the analysis are same, all the things are quite same. Let's see what our regression score says here. So for linear regression, the accuracy score for the for the older for the older data set is 95% in the training, and in the testing data set that is also 95%. So linear regression is actually doing good. And in the feature importances, the feature importance is also same. Like insurance plan is number one, age is like second, normalized risk score is third. And in the rigid regression model, we are getting like 95% accuracy, and then 95% accuracy in our training data set, in our data set. What about XGBoost? So when we are implementing XGBoost for our older data set, we are getting 99% accuracy. Okay, so that is actually huge. And when we are implementing the randomized search CB, we're also getting similar 99% accuracy. Okay, now let's find out like the error distribution, how error is distributed for the older dataset. So when we are plotting the histogram, we can see, yes, we can see that majority of our majority of our predicted values are ranging between -5 and +5 like differences. Okay, and there are some values that are more than 5%, that has more than 5% error, and maximum 15%. Okay, so this is actually completely fine, and this is actually much better compared to our previous distribution. And at the moment, and this distribution is based on 8947 testing prediction scores. And if we want to see the percentage of percentage values that are above or less than actual values, so here we can see that only 29 predicted values that are 10% more than actual values, only 29 rows, so that is 0.3%. So we have a very few extreme errors, only 0.3%, which means this model looks good and no further investigation is required. What this mean? This means that we can actually use the XGBoost model for our older data set, and we can actually push this model into production. But what about our younger data set? Okay, here we the premiums underscore young data set, and we are doing the same kind of analysis here. All things are same. So for the younger data set, our linear regression model is performing very poorly. The accuracy score here is around 60% for the training dataset, and for the testing dataset, the score is also 60%. What about the feature importances? So here, the feature importances, the serial is also changed. Each plan is number 1, okay, but normalized risk score was at a number 3, I think, or number 4, but it went up to second spot, and age actually dropped to like a very low, because for younger people, age has like more discrepancy. And what about XGBoost? So XGBoost is also unable to improve the model accuracy for our dataset, and here the XGBoost is also like 60% accuracy. And when we are actually implementing the randomized search cross validation, the accuracy drops down to 59%. Okay, now let's do the error analysis. So here is the thing. We in the when we are plotting the residual histogram, we can see like very much clearly that the error is actually right skewed distributed. It is actually not like normally distributed, and we can see there are like 80% of 80%. There are a lot of values that we can see that a majority of the predicted values are like more than 20% than the actual value. So when we are considering like 10%, like predicted value is 10% more than the actual values. So we can see that around 4404 predicted value is 10% more than the actual value. What about like so you can just change this threshold to find out the number of prediction values that is actually more, that is actually like that actually has a more error percentages. So in terms of like 10% threshold, we can say that 73% of the predicted value has extreme errors. Okay, and we need to handle them. We will have to discuss about the whole thing with our manager, with our supervisor, and the potential solution could be we will be needing more age data. Okay, at the moment the age data, or like the majority of the age data varies between 18 to 25, and because of that we are facing this kind of problem. So we need more additional data where the age column could be like more nicely distributed. Okay, it could follow like normally distributed, or we might need additional features that could help to improve the model accuracy for the younger data set. Okay, so there could be so at the moment I could think of like two potential solutions, but there could be more solutions. So so what you can do, you can do some kind of research and find out like the more potential solutions. And to find out how we can solve the situation, we will go through a scenario where we are adding a new column or we are adding a new feature. Okay, and we will go through that scenario in our next video. Thank you very much for following this tutorial so far, and if you like the explanations and like the way of my teaching, please do consider liking this video and subscribing to my channel. Thank you very much. See you on the next episode.